How's it going, Kyle?
Going pretty good. Pretty good. How are you, Shad?
I'm doing well. What are we doing today?
Ooh, I wanted to show you something that I stumbled onto, and I think I'll start with a question. Let me see. So you're familiar with Rust and options in Rust, yeah?
A little bit.
Quite.
You and I have been working in Rust for a year, so
I would
at least that familiar.
I would hope so. I would hope so. So my question is, how many bytes do you suppose an option of Boolean takes in memory in a Rust binary?
How many bytes, right?
Hmm.
Okay. Well, a Boolean by itself takes 1 bit, but because of the way that we do memory management in a computer, the smallest thing you can allocate is a byte. So it would be 1 byte for a Boolean. And for an option, I assume an option is probably also some kind of a Boolean because you either have it or you don't have it, and you need
Mhm.
some kind of thing to store whether you have it. So I would guess that an option of a Boolean is 2 bits, which can still be stored in a byte. But I don't know. I don't know if the compiler actually does anything to optimize that into 1 byte, or if it's 2 bytes. Or
Mm,
that's
mm.
my answer.
That's my final answer.
What's the answer, Kyle? Or do we not want to be told the answer? Do we want to discover it?
Let's discover it. So I stumbled onto a cool blog post about it by the name of HereComesTheMoon.net.
Okay.
I've enjoyed reading some of the articles. We can look at the article, or we can go and play with some code. What do you feel like?
Well, you're kind of driving this one, Kyle. I'm happy to code. I'm also happy to just read an article. I guess I'm more inclined to code. Have you already read the article, like in
I
its
have, I
entirety?
have,
Okay.
I
Which
have.
one do you feel like doing?
Yeah, yeah. Let's do an experiment
Okay.
and then pull up the blog post.
Okay. Are we doing this experiment in VS Code?
Yeah, VS Code is probably easiest.
Yeah. Okay.
And nothing special. We can just init a new project.
Okay. Cargo init. We're like measuring sizes of things in memory.
Yeah, yeah, yeah. Looking at some optimizations.
Cargo init memory sizes. Sound good to you?
Sure. Oh, that's great.
It put it on the master branch. Oh.
Let's just hit run and make sure Hello World works. Excellent. Okay, so have you ever used the size of function?
In C, back in the day when you would malloc a struct, you would need to tell it how much memory to malloc for the struct, and you would use the size of operator. But I haven't seen that in Rust before. So, but I'm sure it must exist.
Yeah, yeah, yeah. So let's modify the print statement, and rather than just printing hello world, we can use size of to print the size of just a simple boolean.
Okay, so can I try an idea out then? So let's say I
Sure.
had let my bool.
So size of works on the type rather than an instance of the thing.
I see. Okay, so let's just do that size equal, and we just say size of. Oh, okay, good, cool.
Yep.
Size of.
And use it's after size of before the parentheses, do colon colon, and then the type parameter bool.
Okay,
There we go.
so we got a turbofish here.
Turbofish. I always love that name. I pretty much only use that for like vectors.
I feel like I'm always doing it every time I do some kind of map can collect. The collect operator can collect to many different kinds of things. And so I'm
Mm,
always turbo fishing there.
that's where it is. Yeah, yeah, yeah. On collect.
The reason to know that term, by the way, is that I'm very bad at types and the AI agents are super good at types. So if you just say turbo fish this for me into a vector of int, it will always do the right thing.
I was trying to search how to call new vec and give it the type on the right side rather than let it infer it from the left side of the assignment, and it was terrible. And then I asked the agent, and it was great.
We now have a size,
Yeah, yeah.
u size. Okay.
So let's add it to the print statement.
Sounds good. We're going to print the size of bool is a size.
There we
And
go.
then run that. 1. I'm guessing this is bytes.
1 byte.
Let's do this. 1 bytes.
Okay, okay. Now let's try the
An
same
option
thing,
of
but
bool.
with an option.
Okay. Option of bool. I should have said option of bool. Run that again. Yeah. All right, so we got 1 byte.
1 byte.
Should we
There we go.
should we keep track of this somewhere, you think?
Yeah, just I think just keep writing code rather than modifying the same code.
Oh, good idea, good idea. So I'll just do this. All right, so we got size of bool, size of option bool.
Yeah. Pretty cool. One byte, yeah. So let's try one more one before we talk about how this works. Let's do a U8, an unsigned 8-bit number, and an option of U8.
Okay, so the size of a U8 should be also 1 byte. Should I run it and see?
Yeah, sure. And then do an option U8. And actually, before we do option U8,
Yeah.
what is your guess for option U8 now that you with your new knowledge about option bool?
Knowing that it can. So honestly, I think it would be 2 bytes because I don't know how you would fit the flag of the option into the size of a U8, given that a byte has to use all of the 8 bits. But the way you seem to be foreshadowing, I feel like it's going to be 1 byte.
No, let's run it and see. No.
Okay, no, all right.
You were spot on. You were spot on.
Okay.
So yeah. Now
the function, should I get that in?
Yeah. Let's look at the memory layout. That would be fun.
All right. So we have print memory representation.
And this one takes an instance of the type so that it can also print the actual memory used by that instance.
Okay. We're going to be printing a thing that has 3 variables: the type, the value, and the size. So this is going to be the type, then t is going to be the actual value, and then size is going to be this size of. So we were just using size of down here. Is this the same size of?
Yep.
Okay.
So you might think if you're coming from the Java world, you might think that these bits might not work very well because of type erasure. But in Rust, what it does is, what's the word? It monomorphizes the code. So basically, this print memory representation for each type T that we invoke it with, you'll have a separate function emitted by the compiler.
I see. So what you're saying is that, so after Rust compiles this code, it still knows the types.
That's right.
Okay. Should I modify this code to use your print memory representation?
Yeah, you can modify this code. So just make 4 calls to print memory representation, or maybe a few more than 4.
Okay, let me try it on 1 first, and then I will replace the other 3. So we're going to say print memory representation, and I have to pass it an instance now, yeah?
That's right. So like Boolean true or false.
Okay, so I can pass it true, for example,
Mm-hmm.
and we can run it, and then we see type bool, value is true, size is 1, colon 0, 1.
Yep, so that should be a hex representation of the bytes representing that type in memory, or that instance in memory.
Interesting.
So if you change it to false, I suspect it would emit 0, 0 for the value instead of 0, 1.
Right, so we run it with false, and you're right, it is 0, 0.
You could see it was 0, 0, and 0, 1, so only
Yes.
one of the bits was ever used in a meaningful way. The second bit was not. So maybe we could use that to do something useful, you know?
Okay, let's put this print memory. Okay, so let's put it on a sum of true, maybe?
Yeah, that would be cool.
Let's see what that does. Size of option bool, 1 byte. Type, core option bool. Value is sum of true. Size is 1 byte, and it's 0, 1.
0, 1. There we go. So one more experiment. You look confused, which is fun, you know?
I am confused because where is the encoding of the option?
Yeah.
Okay.
Good question. So there's one more thing we can check, maybe to uncover this. What's the opposite of sum? None. Let's try a none option. And I think you might have to do. I did it via assignment so that you can tell it what type the none is. You could probably do it in line in some way, but
okay. Let's do optional bool colon option of bool be equal to none.
Yep.
And let's pass that instance to here.
Exactly.
All right. 0, 2. Interesting. So 0, 2 would be 1, 0 in binary. Okay. Maybe the way it's doing it is sort of the first bit is either like sum or none, and then the second bit is the value.
If we imagine 2 bits and one bit is used to encode true or false, and one bit is used to encode sum or none. So I think the none is 1, 0. Sum of false was 0, 0. Sum of true was 0, 1.
Let's try sum of false then. Interesting. Okay. So sum of false is 0, 0. Sum of true is 0, 1. And none is 0, 2. Okay. Interesting. None is 0, 2. Okay. I'm going to put a 0x right here. That will tell our viewers and us that it's actually hex. I kind of want to put my terminal over to the right here because that uses our space a little bit better. What do you think?
Yeah.
So we've got this. Should I do a print memory representation of a U8?
Yeah, sure. I think that would be fun. I think it makes sense now how the compiler has managed to represent an option of bool with 1 byte, yeah?
Mm-hmm. For this U8, do you think I should use a big number like 250?
Could be cool. So U8 is an 8-bit number, so we expect it to consume an entire byte, right? At most.
Up to, yeah. Because it's unsigned, it should be from 0 to 255.
Yeah. Let's do 255 just so we get we can see all the
ones.
We can see our hex representation work well.
Oh yeah. So we should see 0xFF. All right, sounds good. Big U8, and then that will be a U8 equal to 255. And then we'll put that here. And I'm going to just jump right ahead to the option here too. Yeah?
Let's do it.
Optional big U8 is an option of U8. And this is going to be sum of 255.
Mm-hmm.
And let's not forget to print it. And do you think I should remove the old bits of code or leave it for now?
You can delete them. I think it'll unclutter the terminal.
Yeah, okay.
Output a little bit.
Let's remove all this older stuff. Size. All right. Run. Okay. Here we go. So type U8, value 255, size 1 byte, hex representation 0xFF. And then now we have an option of U8, sum 255, size is 2 bytes. And now here are our 2 bytes. The first byte now contains a 1 and our 0xFF. Okay.
Yeah. And if you want to try none with the U8, we can see how it represents that as well. I think we can probably guess.
My guess would be that it is still 2 bytes.
And that makes sense. Like it's allocating, you might allocate something onto the stack with an option and you don't know whether it'll be sum or none, and they need to be a fixed size. The compiler needs to allocate a fixed size for it.
Run.
There we go.
Oh.
Interesting. 25. Run it again. Let's see if it's consistent. I don't know where 25 comes from. But
do you really not know where 25 comes from?
No, I really have no idea. I suspect it's not just garbage, but it's probably, I don't know. It's probably just garbage. It's probably always 25. I don't know.
I'm rerunning it a couple times here, multiple times. That's 25.
Always 25. So don't know.
Why is it 25? Hey internets, Future Shad here. The reason for the 25, well, Kyle was right. It's basically just random. Yeah, I reran the program a few times. Here's a screenshot. And if you create multiple U8s in the same style and print them all out, they each have different numbers there. So my best guess is that it's not setting those values to anything. So whatever happened to be in memory at the time, that's the value that it took on. Okay. I mean, okay, it doesn't matter what it is, but 25 is odd.
I would have expected like 0, to be honest. There's one more cool thing that I think maybe you'll know the answer to now. There's a type, have you ever heard of non-zero U8?
No.
So it's an unsigned integer, but it can never take on the value of 0. So can you do this experiment with sum and none, but instead of U8, do non-zero U8.
Non-zero U8.
It's a type that you should be able to import from the standard library.
Okay.
Unsigned 8-bit integer can be 1 to 255, but it cannot be 0.
Is this the one to import?
Down below there's a non-zero U8.
Oh, okay. Got it. This one here.
Yeah. And make this option.
Okay. Option non-zero U8. I think, okay, I see where we're headed. So let's do a sum of 255 again.
Yeah.
Okay, and then let's grab this guy and let's print the non-zero U8 and run that.
And I think you can do maybe into or you can do non-zero U8 dot new, I believe.
Non-zero U8 : new 255 like this.
Yep. And it returns an option already. So if it's out of bounds, I think it'll return none if it's 0. Okay. And then just do your assignment trick and do none. Okay. So before you run it, can you
want me to guess?
can you imagine? Yeah. First guess. Yeah, guess. What's your
Oh
guess?
yeah. Well, I mean, there's an opportunity for optimization where there exists one possible number inside of this byte, the 0, that could represent the none version of the value.
That's right.
So I'm guessing that the goal of providing a non-zero U8 in the standard library is to allow for the 0 to represent the none. So 1 byte.
Good guess.
And I would guess also that when we print the memory representation for none, it's probably 0. The other option it could be is that all the numbers are mapped to 1 minus the value. So like 1 is actually 0 and 2 is 1, but that would be very strange.
Especially,
because,
I think you can do bitwise operations
it would break those.
on numbers. So yeah, I think the bit representation of numbers is like part of the spec, I believe. Okay, let's try it.
We got an option of non-zero U8, sum 255, 1 byte, 0xFF. And the none value is, in fact, a 0. Mm-hmm.
Excellent. That's very cool. So I think that's a good segue to look at the blog post we can pull up. And you called out the way this optimization works here is there was a value that is never used normally to represent an instance of this type. And so the compiler is able to reuse that for its own purposes. In this case, to represent none of an option.
So when we originally started going down this path, I didn't expect that we would be using a whole new type. I thought that we would be getting some free optimizations here and there. This doesn't look free to me in the sense that somebody had to make a bespoke type to handle it. But the magic that I'm sort of seeing is that the magic from the compiler, that is this option around the type. The option isn't built into the non-zero U8. It is exposed from a type that wraps it. That's kind of interesting.
Yeah. I think you're right. I guess if Rust had built in non-zero U8 as a standard type, then you wouldn't need this non-zero U8 in like a num library. I think that was a bit too probably niche for them to expose as a standard type. Like the number of people who want a non-zero U8, it's pretty slim. Now pull up the blog post and you'll see the name of this optimization.
Okay. Blog post open.
So the premise here is a little bit different than what we went through. I thought I would leave another interesting experiment for the blog post, but how many options fit into a Boolean? I liked the name here. I tried to foreshadow by saying the word. It's a very narrow niche to be a programmer who wants to read about options fitting into Booleans. But the way the compiler optimizes is by reusing an unfilled niche.
Okay. So what should I do with this article?
There's some code down below that explores something a little different than what we touched on. So the question here is, how many options fit into a Boolean? And TLDR, exactly 254 options fit into a Boolean.
To be clear, for anyone else watching, what they mean is, given that a byte can hold a Boolean, if you wrap that Boolean in option, you can wrap it 254 times.
That's right. So, and it still only uses one byte. You can see on the right side of the screen you're on, it does nest bool 254, and we see 1 byte. So that is 254 levels of nested options. And then the next line, 255. And then I like the wording from the author of this article. If you scroll down a little bit, it turns out that option bool takes up exactly 1 byte of memory, the same as bool. Pretty cool. That's what we observed as well. The same is true for option bool, all the way up to 254 nested options. And this is the line I like. At 255 nested options, the compiler finally relents and requires a wastefully decadent 2 bytes to satisfy our sick desires. I was like, ooh, this author, I like this author.
In an alternate universe, he was a writer of stories. This nest here, is this a built-in macro, or did he write a macro that does this?
They wrote a macro. It's down below on the left. We can view the macro. Macros, my intuition around the syntax is terrible. Claude did an excellent job. I pasted this macro in, and it was even really badly formatted, and Claude's like, we think you're trying to do this, but the formatting got busted, and it like reconstructed the original macro and then explained it to me, and it was It was spot on.
Yeah, this is a little bit above my head. For the purposes of a blog post, this is great. For our purposes, though, Kyle, we could run this.
We can use the macro. We can also just copy and paste a bunch of options, and do it the old school way.
That's my way. Let's do it. So they are not using instance.
This is just doing the size, not the memory representation. But we can do an instance and.
Okay, let's do that. All right. Let's call it nested options. Okay, nested optional bools. Yeah?
254 and then watch it roll over.
So I think we can leave it equal to none, right?
Mm-hmm.
And we should still see 1 byte. Okay, still 1 byte, whose value is 3. Yeah?
3 is interesting, right? Like we saw before when it was just one option that was none, it was 2.
Now I kind of want to see what 3 option of bool is first.
Let's do it.
All right, so
4.
we went from 3 to 4. Yeah.
Ooh, this made sense.
These types are going to get nuts. I'm going to actually remove it from the print statement because otherwise we're just going to get a giant.
Yeah.
Let me make sure it's not broken. Okay. Yeah. Unfortunately, we don't get to see anymore what it was. I'm going to delete the top part so that we're just looking at our option of bools now. So here we actually still have our first option of bool. I'm going to keep that because that was good. And we're going to drop the rest of this. Okay, so this one here was a bool with 3 options wrapped, yeah? Okay, and it was 4.
Interesting. It's like having my human knowledge of options. It's like no matter how many options I have nested, it's still either some or none. Like as a human, I believe I could optimize an unlimited number of options and still only use 2 bytes with no loss of representation. Yeah.
Because the values that this can take on now are none, sum of none, sum of none.
Ooh. Okay. I was mistaken. Yeah. I was somehow duped into thinking it would either be overall none or some. But you're right. It can be sum of none. Yeah. Makes sense. Like the author of this blog post calls out that it's pretty useless. Like you almost never nest options in practice. Like you either have a value or you don't.
Yeah.
But an option is just a 2-variant enum, and so this optimization can generalize to other kinds of enums as well. Finish the job here. I want to see 255 options. It'll take you 30 seconds to double the number. Okay. I think.
All right, sure. All right, so we have 3 here. Now we have 6, 12. I should not have done 3s. I don't know my multiples of 3s. Hold on, we're doing 2s.
Yeah, when you selected the third one, I was like, 3? What kind of crazy person am I talking to here?
We're going to do 2. We're going to do 2. Okay, 4, 8, 16, 32, 64, 128, 256. I'm going to just trust the editor now to tell me when it's not actually highlighting. Okay, no good.
A few moments later.
1, 2, 3, 4, 5, 6.
Ooh. How many was this? Is this 255 or 254?
This is 256. This is 256 because doubling. Okay. Overflow evaluating the requirement. Consider increasing the recursion limit.
I didn't know that was a thing.
Just learned a new thing.
Attribute to your crate memory size. Okay. I'm okay if my sick desires are left unsatisfied.
No. It might just be 256. Let's remove it. Let's just remove 1 and then see. We might be fine. No, 255 is a problem.
I mean, what is that recursion limit 256? To your crate, how do I apply a recursion limit? Ask your agent to fix it.
How do I add? Oh, that was it. Just needed to add it at the very top of the file, right here. Recursion limit. Thank you, agent. That was very helpful. All right, this should take 2 bytes.
2 bytes, agreed.
2 bytes.
Now, if we delete one of them and have 254, we should get the nice experience of saving 1 byte.
Okay, here we go. Yeah, you're right. 1 byte. Very cool. Okay. Now can we do a struct of enum?
Yeah. Let's do it.
Let's start with an enum. Let's call it meat. Chicken.
Interesting. Yeah, I had tried enums that have values for fields. It'll be fun to see what this does.
So we got an enum meat, enum veggie, and then we got some carrot, and we have some broccoli. broccoli, cabbage. We got 2 enums, Kyle. Now let's have a struct.
A struct or an enum? I also want to try an enum that contains both.
An enum that contains both?
Meat and veggie, like a food.
Oh, that unions the 2 enums together?
Mm-hmm.
Oh, okay. Here we can have a dish that contains a meat and a veggie. So meat is a meat and veggie is a veggie. And now what I want to do is know the size of this dish. All right, so let dish equal a dish, and then we're going to have a meat be a, you want beef? Sounds good, Kyle. And a veggie, what would you like?
Cabbage.
Some cabbage? You got it. And now let's print the memory representation of your dish. It doesn't like it. Why not?
Derive debug.
Pound square bracket, derive, debug.
Yeah, and you'll have to put that on the enums as well.
All right.
Excellent.
Let's run this guy. It's going to be some warnings. 2 bytes, Kyle. So we don't get an optimization there.
No. Now, if you combine them into an enum, like a food, just say food, and then we can have a variant that you call veggie, comma, and then do the same.
Okay. All right. And now we have a let food be a food, and then we do a meat of meat chicken, and then we print food. Run. Could not compile memory sizes. Debug. Whoops. One more time. Run that. Still 2 bytes. I'm a little surprised.
Right? Like plenty of niches to optimize into there, I think. Pull up. I'll send you another post talking about this, and we can look at it. So I'm not trying to handwave too much code. So this article also touches on the niche optimization in Rust, but it focuses on enums.
Enums are one of the most popular features in Rust. An enum is a type whose value is one of a specified set of variants. Here we can have a foo that is either an int or a char. Values of type foo are either integers, example the variant foo int3 with a payload of 3, or characters, example the variant foo char a with a payload of a. If you think of structs as being the and combination of their fields, enums are the or combination of their variants. This post is about a surprising optimization that the Rust compiler performs on the memory representation of enum values in order to make their memory usage smaller. Spoiler, it's not the niche optimization. In general, keeping values small can result in faster programs because values get passed around in CPU registers and more values fit in single CPU cache lines.
And the next paragraph is kind of interesting. Generally, the size of an enum is the size of the largest payload, plus some extra bytes for storing a tag. So that's what we most of our types that we've been working with so far have been 1 byte. So we really haven't had to think about that. But because it's an enum is the or of all the variants, the compiler it doesn't need to store all of them simultaneously. It just needs to allocate enough memory to store the largest variant. If you scroll down, we can see a representation of one of the enums that they wrote above, an enum that has an int and a character variant. And you can see how the first bytes are used as the tag, and then there's the value allocated.
That was not what we saw.
Ours was for a 1 byte variant.
So what is a tag?
A tag is at runtime, it says what variant is contained in this memory. So you can see this one has 2 variants, and so there's 0 and then 1, but you could have more variants represented. I think if you scroll up a little bit, it tells us the answer on why it allocated more. Both variant payloads take up 4 bytes, and we need an additional byte for at least the tag. A requirement called type alignment requires that Rust actually use 4 bytes for the tag.
We could test this out because we could just copy this enum and then see. So if I were to put this enum here and then I were to print the memory representation of 5, what do I get? Okay, and it's the same, yeah? 0. Yeah, so it is in fact using 4 bytes for the tag.
If you change it to a U8 instead of a U32 on line 41, I bet you it'll just use 2 bytes total instead of 8, because a char is one byte, right?
And a U8 is also a byte. I think if type alignment means that things come in powers of 2, then 2 bytes. Let's go. Still 8.
Still 8. Change char on line 42 also to U8.
Oh, wait, a char is actually
4 bytes.
Yeah,
4 bytes?
It is, yeah. Because it's not an ASCII char. It's a Unicode char. Yeah, okay. 2 bytes.
And yeah, if we make it U16, then I speculate we will use 4 bytes total, aligning to powers of 2. 2 bytes for the largest variant, and then 2 bytes for the tag.
4 bytes. Agree.
Okay, we understand. Nice. They have another experiment in this blog post down below that does talk about the niche optimization. This next one, beyond the niche optimization, it shows an inner enum with two U32 variants, and then 2 code blocks down, it shows an outer variant, an outer enum that contains the inner enum and another variant. So it'd be fun to try these.
Hold on, let me wrap my head around what we're doing. Okay, so we have an enum that has either an A U32 or a B U32.
So that'll take 8 bytes.
That'll take 4 bytes for this, or 4 bytes for this, and then 4 bytes for the tag.
Yeah, to align on, we think powers of 2. I don't actually know what the rule is for it, but I think it's proved true so far.
Here we're talking about things like 12 bytes though. So, okay, so now we have this outer that is either another integer or A or B. And so D would be A or B. Okay, my guess would still be 8 bytes. Okay, he says that he would guess 12 bytes, but it's not. Values take up only 8 bytes. Well, my guess for it still only being 8 bytes is that within the tag, you can represent whether it's a C or a DA or a DB. Those are the options.
Yeah, we can repurpose some memory representations of the tag allocated for inner to capture the variant of outer. But if we were naive, we would say inner takes 8 bytes, and then we need at least 4 bytes for the U32 in variant C. So max of 4 and 8, we have 8, and then we need another byte for the outer tag, and then we have to, apparently it's not powers of 2, it's multiples of 4 maybe?
Multiples of 4 unless it's 2.
Oh yeah, multiples. Okay. Maybe multiples of 2 then?
Yeah, well, that doesn't work because sometimes it should have been 6 in our experiments, right? We've had a few experiments where it could have been 6, and it didn't.
Oh, yeah, it went up to 8 because we had a 4 byte and then a 1 byte tag. Okay.
You want me to ask the Jippity?
About type alignment? I think we have the keyword.
In Rust, what is type alignment in terms of
memory layout?
Of enums? I'm specifically curious why sometimes things take 8 bytes when it appears that they can take 6.
Yeah. It kind of makes me want to go in and add some optimization to the Rust compiler, but I'm sure lots of folks have thought about it.
Okay, the AI thinks that alignment is always a power of 2.
The guy, he would have guessed 12, but it's actually 8. So it's like you would have guessed 12 if you don't factor in type alignment. So I think powers of 2 is still accurate. We haven't seen a violation of that. But it's weird. Alignment is always a power of 2. Like, I don't know. It seems
wasteful after some point.
Yeah. You're like, I want to allocate a few more bytes. Just allocate like another word.
Well, we could also test that. Okay, here's what we're going to do. We'll make a struct that contains 4 integers. 4 integers would be
4U32.
That's 16 bytes.
Yeah, and we could just try adding another U8 to the struct.
Okay, let's give it a try. This file's getting large. I'm going to delete stuff, Kyle. Let's start with the struct. All right, so our struct is going to be a 20 byte struct, 20 byte struct. And then it's going to contain an A integer, which is of type U32. So that's 4 bytes, B, C, and D.
They're up to 16.
And then we're going to have a Z that is going to be a U8, which is only 1 byte.
I thought you said 20 byte struct. You're up to 17.
Yes. So now I'm curious where we get alignment on this 20 byte struct.
Well, the struct is only 17 bytes, right?
Right. So we're 1 byte over the 16 byte alignment.
I see. Okay.
Right?
Yeah. Sorry, I was just thrown by the 20 bytes. Like, it's like the struct only needs 17 bytes in theory. It's just...
Oh, sorry. Wasn't thinking. 17 byte struct. Okay, thanks.
Yeah.
All right. Print the memory representation of the 17 byte struct.
Debug.
Yep.
Always debug.
Always the debug.
They need... I'm surprised in VS Code, I want a autocomplete, like command dot option to derive debug display, like common stuff. Even here, if I have a implementation of a trait and I forget to implement some function, I can say command dot and add the implementation.
I think it does do that. I just ignore it. Let me see. If you go here, no. I thought I sometimes see like a little, this thing here. Click. Add the derive.
Okay. Like, I want down on the error. I want it in context. Just like, yeah. Add the debug.
Let me try. Quick fix. Okay, no, that's going to use the AI. Hold on.
Like, letting the AI do it is fine. But
yeah.
I guess it's fine.
This is fine.
It's fine.
It's fine.
It's not as fine as it could be. I agree with you. Okay, let's run.
Okay. Size 20. So not powers of 2.
Not powers of 2.
Not powers of 2. It's got to be multiples of 4, you know? Like if you make add a field E to have 21, and I'm dead certain it'll be 24 will be the size.
Okay, so this is a
21, yeah. Sure.
21 byte struct. E is 0.
24.
You're right,
Okay.
24.
Multiples of 4. It makes sense. It's what I expected. It's like word alignment.
Yeah, word alignment, with the exception of like 1 and 2 byte things. So like you can have 1 byte things, you can have 2 byte things, and then 4 and above, it's always multiples of 4. All right, that was fun, Kyle.
I came away understanding even more than I came in knowing, for sure.
Thanks for hanging out with me and doing this thing.
It was fun.
Okay, well,
Okay, Chef.
on that note,
I will stop this recording.
okay, bye.